Greetings, and thank you for joining our session. My name is Peter Morehouse. I have been with Smitt for over 12 years, working with electromechanical relays, circuit breakers, and sensors. And I'm excited to lead you through this webinar. This short educational session will be followed by a question and answer period for anything that may come up during our presentation. The topic of today's webinar is about how train operators may increase railway relay life expectancy. We will also provide an overview of the principles of robust design of relay circuits. With that, let's begin. First, why is this webinar important? The answer is simple. As we produce relays as integral parts of electrical engineering systems, train operators may face intermittent electrical control failures that occur on board. As these failures occur, it is easiest to blame the relay. But everyone must remember that reliable electrical control is all about choosing the right relay for the right application, as well as creating optimized switching conditions. This ensures that relays survive their full life expectancy and even as long as the train life expectancy. The end result is low life cycle cost. Let's take a look at an example. One day, a train operator called. "One of your relays is not working. It seems like the contacts are sticking. The relay is no good." Initial inspection indicated a pip and crater effect, as you can see from these photos. This effect resulted in sticking contacts. So, what causes pip and crater? It is the expected result due to frequent inrush currents affecting the material contacts. Further investigation of the electrical schematic provided by the customer indicated that the inrush currents were caused by LED light switching. Frequent, short duration, high inrush currents are a normal LED side effect. So what can customers do in order to prevent this from occurring? There are two possible solutions. First, install a thermistor in the LED switching circuit. It will prevent the inrush current, but the thermistor requires periodic maintenance due to a short life expectancy. The better solution may be to substitute a relay that utilizes a hard relay contact material. Silver tin oxide is the contact material used by Smitt. It will withstand inrush currents, maintaining long relay life, and does not require maintenance. For example, we offer our relay series BK400 and D-U200N with this relay material as an option. To further explain, let's take a look at what is actually happening to the relay contacts. First off, if you look under a microscope, you will discover that the contact surface is not flat. In fact, you will see small contact points through which the current conducts. These small areas of the surface carry the current, while softer material flattens out. Another occurrence is that the contacts become polluted over time, forming a surface layer. Both because of oxidation and due to organic deposits, the older the contact, the worse this surface layer will get. Gold contact plating is utilized to prevent the formation of oxides on the contact surface. The second thing about the physics of the contacts is, to create a conductive path, there must be a minimal contact pressure between opposing contacts in addition to a minimum voltage and current. Voltage creates conductive pathways called A-fritting. Typically, the minimum value is above 1 volt. Depending on the surface layer, the thicker the layer, the higher the required voltage. As current starts to flow, it creates a conductive area that has the name of befritting. As you see from the image on the far right, a higher current creates larger contact spots, lowers the voltage drop, and leads to lower contact resistance. Now, let's look at what happens during the switching of the relay. You can see the contact push and wiping action. This wiping action removes surface layer pollution from the contacts each and every time the relay is cycled. This flattens the contact surface and increases overall contact surface area. The outcome? Improved conductive pathways. The conclusion is that a regular wiping action or mechanical contact cleaning is important to the health of the relay. This time, let's look at electrical contact cleaning. Do you see the spark between the contacts? The energy from the spark during making and breaking contact loads burns away the surface layer. Higher energy cleans more than lower energy. Thus, electrical removal of contact pollution leads to a thinner surface layer, again, creating better conductive pathways. The combination of electrical contact cleaning and mechanical contact cleaning minimizes contact resistance to ensure proper electrical conductivity. Here is a visual representation on how best to optimize relay life. As we have already reviewed, and using a standard contact material like silver for this example, too high of a current causes a pip and crater on the contact, displacing contact material and shortening the life of a relay. Too low of a current and we risk a thick surface layer which prevents electrical pathways. To ensure perfect relay performance throughout the predicted life of the relay or system, we need to understand the sweet spot. We at Smitt define the sweet spot to be between 20 milliamps and 500 milliamps. Designing a relay circuit within this range guarantees the most robust electrical criteria for relay use. However, there are applications that are outside of this sweet spot. For these applications, we must consider other contact materials to prevent relay failure or truncated life cycles. For example, we can utilize gold for communication or other dry circuit examples that normally fall below 20 milliamps and even as low as 1 to 5 milliamps. In the case of inductive or capacitive loads, including motors or solenoids, we can consider silver tin oxide contacts, which, as you may recall, are harder than silver and resist material displacement to ensure longer contact life expectancy. Remember, reliable relay switching over long periods of time must have sufficient electrical and mechanical cleaning operations. Always consider the type of load, know the minimum voltage and current to ensure proper relay contact conductivity, and schedule periodic inspections and replacement of your relays as different electrical parameters and duty cycles will have significant effects on how long a relay may be expected to last. Here are a few additional relay facts that may help you better design your circuit. An alternating current, or AC load, is a sine wave which crosses back and forth through 0 volts, and the current stops automatically, making it easy to break a contact load without damaging the contact. A direct current, or DC load, on the other hand, is more challenging as current is present continuously, resulting in the spark seen on a previous slide. This can often result in electrical arcing between contact surfaces as two opposing contacts begin to open. For resistive loads, we experience currents and voltages without surges. In the case of inductive loads, voltage surges occur and result in arcs between contacts. Finally, with capacitive loads, contact making happens at peak inrush current. These latter two cases result in the greatest potential for contact material displacement, and the consequence is a much shorter expected electrical relay life than one would find in a resistive load application with the exact same voltages and current levels. So how do we prevent surges? First, single contacts are typically used for normal contact loads. Double make, double break contacts are used for high DC inductive loads. Contacts wired in parallel are used when the making of the contact is most important and/or the circuit has low-level contact loads. Once this contact configuration is determined, proper coil protection should also be selected. If surges are generated by a coil, a diode protects the control circuit, whereas if surges are generated from the application, a varistor or double Zener diode protects both the relay coil and the control circuit. We can now examine how to maximize braking capacity and contact life. The video on the left is without a magnetic arc blowout in the relay. The large flash, or arc, exists because there is no outside mechanism to extinguish the arc. In other words, the arc is maintained until the contacts are physically far enough apart to prevent further current flow. The longer the arc exists, the more contact material is displaced, and the shorter the life expectancy of the relay. It should be noted that with enough energy, there may never be enough distance between the contacts to ever extinguish the arc without some external means. The video on the right is with a magnetic arc blowout. The presence of a magnetic field near the arc creates, in essence, a magnetic wind which blows out the arc. Wiring contacts in series and/or a magnet can increase braking capacity of the relay and increase relay life. Please allow me to provide an overview on how relays could be checked or serviced, as reliable relay operations helps to ensure safe and uninterrupted passenger experiences. For train operators, this is a crucial but often overlooked maintenance requirement. Time and budget restraints can impact the attention needed to address relay-related issues. To minimize these impacts, Smitt has developed different service tools which help identify root causes of repetitive or intermittent system failures. One option is our on-site relay condition testing using our portable relay tester. For another, when a train is in service, we can provide relay performance monitoring and fault finding with relay circuit test tools, as well as the manual testing of relay circuits with our D-Test switch relay. If customers conduct relay maintenance independently, our technicians are available to teach or work with our customers' engineers on relay applications or complement their work with on-site test and inspection by our service team. The following few slides are a real-world example that is indicative of the need to conduct periodic routine maintenance on relays. Our service team conducted a top-to-bottom investigation of a major metro's relay condition. This metro had no routine maintenance schedule for relays, and the relays were in daily use for over 9 years at the beginning of our study. The conclusion was a win-win for the customer, as it ensured proper future performance while uncovering some surprising results. Through the process, we observed the following relay conditions. 1. No problems and no actions were needed on a relay. 2. The relay is not appropriate for the application and a different relay is recommended to optimize life and function. Or 3. The relay is appropriate for the application but in need of immediate replacement, or a recommended periodic replacement schedule was determined. Our in-depth review of the relay panel validated the design and assembly in most cases, while in others we found wiring mistakes that could result in safety problems or otherwise would result in better relay performance. At the end of the process, our customer knew precisely which relays would last the train life, which relays needed periodic replacement due to demanding loads and duty cycles. They had greater confidence that the relay train wiring was correct, and train lifecycle costs were reduced due to a low likelihood of relay failure, in addition to their not having to replace every single relay several times throughout the train life. That is a win-win. Smitt offers a variety of services that can help our customers determine the best relay maintenance schedule for their fleets. The simplest and often most direct analysis is to return a sample of safety relays for laboratory analysis. Our analysis will determine the remaining life expectancy and result in a recommendation to replace or retain each relay. At minimum, a scheduled replacement of only the safety relays will prevent the majority of relay-related revenue service train stoppages due to such preventable issues as HVAC failure or door open failure. A second service we provide is on-site relay assessment using our B&D dock tools and other maintenance tools. As detailed in the previous slide, this type of assessment provides a deeper look into the suitability of a relay to its specific application, checks relay train wiring for accuracy, and examines environmental factors which could impact proper relay performance. In both cases, Smitt provides a comprehensive summary of findings with best practice recommendations. As you can now understand, proper relay selection for each application is fundamental to maximizing relay life expectancy, and periodic checking and measuring of in-service relays ensures that all circuits operate predictably every time the relay is called upon. So what's next in relay evolution? For Smitt, it is eliminating the requirement for relay testing and scheduled maintenance and moving to condition-based maintenance. Our latest module provides data about relays' health to enable predictive maintenance and improve system performance before a problem ever occurs. Among other functions, it counts switching loads to know precisely when a relay reaches its predicted end of life. The Smitt relay monitoring system will be presented live this September in Berlin at Inotron's International Trade Fair for Electrical Transport. A few final do's and don'ts. Do not remove the cover of the relay or attempt to repair a relay yourself. Most relays are consumables, as the cost of replacement is often cheaper than the cost of repair and certainly not worth the risk. Power down your circuit before ever replacing a relay, and understand how to properly insert and remove a relay into and from its relay socket. Finally, a well-designed relay circuit can last 30+ years without replacement. However, actual train-borne electrical conditions may vary from the original design expectations, or may even vary from train car to train car within the same fleet. Always have a scheduled relay maintenance and/or replacement plan in place. To summarize our presentation, 1. Consider each relay application during initial design of your relay circuits and during train upgrades, and always consider correct relay contact material. 2. Use silver tin oxide material in relay contacts in case of LED light applications or any other contact load with electronic inputs. And 3. Use relay test equipment and/or service experts to understand relay condition and anticipated replacement dates. This concludes today's session. Please stand by for the question and answer period. Thank you.